Hi everyone, thanks for the introduction. My name is Mustafa Bishimiyasar and welcome to this presentation entitled PQ Cloudization, Rapid Prototyping of Scalable NTT Inverse NTT Architecture to Accelerate Kyber. This is joint work with my colleague in Microsoft Azure. So, in this presentation, we will have a brief introduction about the motivation of this work, some background review, and our contribution. After that, we will discuss about our proposed architecture, and we will see the implementation results and comparison with the previous work for both NTT and Kyber architecture. And at the end, we will have a conclusion and some possible future goals. So let's start with the motivation of this work. As you know, our current public key crypto systems will be broken when we have a large scale of the quantum computers. Therefore, we have to migrate to post-quantum cryptography, PQC, as soon as possible to protect our systems, our communications against both classical and quantum computers. So you may ask, why now? We do not have those actually large quantum computers right now. So why we need actually to going forward in the PQC. So the reason is, although we actually project that the quantum computers would be sometimes in 2030 or later, a few years later, attackers can actually store and collect our current data and try actually to break them when they have those actual computers. Therefore, we have to protect our systems right now. And based on that, NIST has started actually a standardization process since 2016. And after actually several rounds, several candidates and proposal, a few weeks ago, we have actually the first standardization draft, which selected Kyber as the next post-quantum crypto systems. So, in this work, we actually target Kyber, and Kyber is actually a lattice-based crypto system, and we try actually to accelerate and optimize the NTT, which is the most challenging part of the Kyber crypto systems. So there are two main approaches for designing a hardware accelerator. We can use the hand-optimized RTL design, or we can actually going forward with the high-level synthesis tools. So in the hand-optimized RTL design, you have control over lowest level of the arithmetic and operation, which actually allows you to actually have a highly optimized architecture based on your desired optimization perspective. You may actually want to reduce the power consumption or actually increase the performance or so on. However, this approach will limit you from the flexibility point of view, and therefore any change in the performance or configuration would be actually takes a lot of design period, and you need to repeat lots of process again. At the other side, you will have the HLS tools, which gives you a trade-off between the optimization and also the design time. Also, since you are designing your algorithm in high-level languages such as C, it gives you better flexibility, and you can have more scalability in your design. However, it may not lead to the best design from the performance, from the from the optimization perspective. So, and in most of the cases, it requires more hardware resources, which means you need to pay for extra hardware costs. In the RTL design, there are several works, including some of my PhD works, which targets different optimization perspective, such as high-speed actually NTT, high-speed actually design or compact architecture. However, from actually the using the HL space actually design, there is only a few design targeting the PQC implementation. So based on that, we did, in this actually work, we proposed the first actual hardware implementation of the Kyber targeting the cloud platform using the HLS tool. And we designed a highly parallel and scalable entity and inverse entity architecture using actually our method that we will discuss it later to address some performance, complexity, and design period challenges in the entity in the lattice-based cryptography. Using our accelerated entity, we can we can use it in the Kyber and other entity-based PQC algorithms, such as the fully homomorphic encryption on cloud actually infrastructure and services. So our results show that we can achieve 11 times performance improvement using our accelerated entity, which needs only 14 cycles to compute entity operation with the Kyber parameters. However, these performance improvement achieved at the cost of around 4 times more resources, which still achieves 63% efficiency improvement. From the Kyber perspective, using our accelerated entity design, we can actually perform a key generation, encapsulation, and decapsulation operation in 7, 11, and 15 microseconds. So this is the Kyber protocol. The Kyber actually has 3 main operations: key generation, encapsulation, and decapsulation. There are some public parameters that Alice, as a first actual part of this communication, used those parameters to create and generate her own secret key and public key. These 2 values. So after that, Bob will use the Alice's secret key, public key, to encapsulate the message and generate the shared secret key and also a cybertext CT. The CT will be sent back to the Alice, and Alice will try to decapsulate the cybertext using her own secret key to regenerate the shared secret key. Using this shared secret key, these 2 actually parties can communicate to each other through other crypto primitives such as the AES. As you see here, there are several actually submodules for the Kyber, and the most actually challenging, as I mentioned before, is the entity, inverse entity, and pointwise multiplication. And in this architecture, we try to implement only one set of these submodules, and we actually generate and design a unified architecture to support all these parameters, all these actual operations. Sorry. So this is our actually proposed architecture for NTT, which has multi-level optimization. So NTT is similar to FFT in finite field, which we use it for the polynomial multiplication. The polynomial multiplication cost and complexity is n for polynomial of degree n is n squared, and using the entity we can actually reduce it to n log n. So the entity is an iterative operation, and in each iteration we need to perform a sequence of butterfly operation over the polynomial coefficients. Each butterfly takes 2 polynomial coefficients and tries to combine them with the trivial factor and generate 2 outputs. So for a polynomial of degree n, you will need n divided by 2 butterfly operation in each stage, and we need actually log n stages. So in this architecture, we have several actually optimization level. In the core level, we design a reconfigurable butterfly core, which can support both CT and GS configuration which needs in the NTT and inverse NTT operation. Using actually this reconfigurable butterfly core, we can actually support both those operations. And then we have several of those butterfly core parallelly implemented in our design. The number of the butterfly core can be set by user, which gives us a trade-off between the resource utilization and our required performance. The other things is there is in the stage level, we have a data dependency between stages. It means that the output of stage 0 would be the input for the stage 1. And for that, we actually design an entirely stage architecture, which we only actually implement one stage, and then the output of the stage will come back again as the input for the next stage. The butterfly core, as you see here, has a two actually a set of the registers as the input and output, and this latency of the butterfly would be 2 cycles. Using actually this technique and by reusing the embedded buffers in the butterfly core in the stage architecture, we can reduce the required resources in our design. So at the very first actual cycle, we feed the polynomial coefficients in the architecture, and after that, we actually the results will come back again to the stage architecture until we compute all actually remaining stages. In the polynomial level, we know that most of the lattice-based crypto has more than one polynomial to be converted in the entity domain. For that reason, we have a pipeline architecture that will fit the next polynomial after finishing the last stage of the current actual polynomial. Okay, using this actual multi-level optimization technique, we achieve a significant improvement compared to previous work. So comparing to the previous HLS-based architecture, we can achieve 3 times speed up per core, these actually blue bars, and also having more parallel cores, we can achieve 11 times more throughput, total throughput, compared to the previous actually HLS-based architecture. Again, it achieved at the cost of 4 times more resources. Compared to the hand-optimized RTL design, our results per core would be almost comparable with that architecture, the base architecture. However, using those actually parallel architecture, we can achieve almost actually 50 times more speed compared to the those architecture. We use actually our NTT hardware, actually our accelerated NTT architecture to implement the Kyber 512 design, and the results for key generation, encapsulation, and decapsulation operation is shown here. As you see here, using 2 different configurations with 64 and 128 actual cores, we can achieve a significant improvement compared to the previous work. So our results show that we can achieve 33%, 5%, and 20% performance improvement for key generation, encapsulation, and decapsulation operation. However, if we compare our result with the previous HLS-based architecture, we can see a significant actually improvement, which is around 40 times better actually throughput, even with less resources, which is great. So now I want to actually discuss with you about the design effort and complexity of our design using the HLS tool. So for any actually designing the hardware accelerator, there are several stages that we need to actually take care of them: software modeling, hardware design, optimization, verification. The software modeling would be the same from the design effort actually and design period time in both actually. In both approaches. However, the HLS can reduce the required time for the hardware designing, optimization, and verification. At the same time, HLS actually can provide us more flexibility and scalability in our design. To be specific, we compare our NTT and Kyber architecture with the previous work. As you see here, our HLS would be actually very, it needs actually very reduced time to be implemented and designed compared to manual RTL design or RISC-V architecture. It also provides us a unique degree of flexibility which is required for the cloud platform to service different applications. From the Kyber architecture point of view, you can see designing a Kyber with 2 or 4 butterfly cores would be very needs lots of time. However, we can achieve a design with 128 butterfly core with less time. Okay, to conclude, we need actually move forward to post-quantum crypto implementation as soon as possible, and we can use the HLS tool to accelerate the prototyping stage, particularly when the resource utilization is not your main concern. So in this architecture, in this work, we prototype a Kyber implementation, targeting the cloud platform, and we actually address some challenges, including the complexity, design time, and performance, using our accelerated NTT architecture. Our NTT architecture can outperform the previous work with more than 11 times speed up. And from the future work point of view, we need to investigate our design with side channel analysis attack and embed some possible countermeasures. And also we need to optimize our design from the resource usage point of view and try to make it more closer to the RTL architecture. Thank you.